right, let's do this. This is 7.1. If you're here, you've made it past the first test, right? Yeehaw. Now we actually start learning trigonometry. Okay, today's pretty simple. We just go over angles, degrees, radians, and other stuff that's involved. So first page is purely definition. Talks about what an angle is, and when two rays are drawn with a common vertex, they form an angle. We call one ray of an angle the initial side and the other the terminal side, as you see in the pictures below. If the rotation of the angle from the initial side to the terminal side is counterclockwise, the angle is positive, which you see here. So if we rotate counterclockwise, that represents a positive angle. If you rotate clockwise, then it is a negative angle. An angle is said to be in standard position if its vertex is at the origin, meaning the center 0, 0, right? And its initial side coincides with the positive x-axis. So you see how these are all set up. You've got an initial side, terminal side, initial side, terminal side. So those are the components of an angle, a positive angle, and a negative angle. All right. When the angle is in standard position, either the terminal angle will lie in a quadrant, like the above ones, like they were in an actual quadrant, or the terminal side will lie in the x-axis or y-axis. These are called quadrant angles. So this one is on the y-axis. The terminal side is on the y-axis, and that makes it a quadrant angle. Okay. All right, so those are definitions of what angles are, what type of angles you have, positive, negative, or even a positive quadrant angle. You can have a negative quadrant angle as well. All right, the definition of degrees: the angle formed by rotating the initial side exactly once counterclockwise. One revolution is said to measure 360 degrees. So if you were to draw this and you had the initial side, and then the terminal side, you rotate it 360 degrees where it meets up with the terminal side, with the initial side, then this would be one full rotation at 360 degrees. So that's one revolution, right? You meet back up at where you started. And that could go for any angle, right? Let's say we had the initial side there, terminal side here, and then we go ahead and rotate this angle 360 degrees, and we land back on the terminal side. So we went 360 degrees, and we still end back up on the terminal side. So that is one revolution. Okay. So 1 degree would be 1/360th of a revolution. 90 degrees is a quarter revolution. 180 degrees is half a revolution, and 360 degrees is one revolution. All right. I guess I could represent these. I have enough time. So 1 degree, let's see. So there would be your initial, and then there'd be your terminal, and there'd be your 1 degree. "90 degrees, once again, your initial, and if you rotate 90 degrees, there's your terminal side, which makes it a 90-degree angle, which is a quarter of a revolution. And then 180 There's initial, and there would be terminal, because we rotate half, right? 180 degrees, half a revolution, and then here you would have your initial side, and then to get to 360 degrees, of course, rotate 360 degrees, and we land on the initial side again. Okay, that was one full revolution, right? All right. So down below is just practice in drawing an angle. All right. So we want to draw 45 degrees. So when we draw 45 degrees, we first want to list the quadrants that we're in. So this will be, zoom in a bit. Okay, so this will be 0 degrees. And then if we go counterclockwise, you'd have 90 degrees, 180 degrees, 270 degrees, and if you do one full rotation, this is also 360 degrees. So all we want to plot is 45 degrees. So 45 degrees would be in the first quadrant, because 45 is between 0 and 90. So to draw it, well, I put the initial side here. There's the initial. And then 45 degrees, cut straight through the middle, because that's half of 90, right? There's terminal. And there's 45 degrees. Maybe not so big. There we go. Okay, and that's it. That's drawing an angle. Let's try it again. Negative 90 degrees. Once again, label everything. 0, 90. Don't forget your degrees. 180, 270, 360. Now, negative 90 degrees, remember a negative angle goes clockwise. So if 90 is up here, the negative 90 must be down here. So once again, there's the initial side, terminal side, and then negative 90 degrees. All right. All right, 225. Label 0, 90, 180, 270. Initial side always over here. And then 225, you guessed it, is between 180 and 270. So that is just straight through the middle again. And this is our 225 degrees. All right. And then 405, 0, 90, 180, 270, 360. And if we are graphing 405 degrees, well, first, here is the initial side. And 405 is definitely over a revolution. It's over 360 degrees. So this means that when we graph 405, we do 360 degrees, and then we have to go an extra, whatever 405 minus 360 is, that's 45. So we go an extra 45 degrees. So this would be your 405 degrees. That's it. Drawing angles doesn't seem so bad, right? Definitely not a test question. This is just practice in locating what quadrant you're in and where your angles belong. Okay. So we had the definition of degrees, and now we have the definition of a radian. A radian is a central angle. A central angle is a positive angle whose vertex is at the center of a circle. The rays of a central angle subtend or intersect an arc on the circle. So that's everything that's going on in this picture below. So we have the center of a circle, and that the rays, the initial side and the terminal side, both intersect the arc on this circle. If the radius of the circle is r, and the length of the arc intersected by the central angle is also r, then the measure of the angle is 1 radian. And of course, I have my in English definition. If the arc length is equal to the radius, the measure of the central angle is 1 radian. Okay. So I wouldn't worry too much about all of this lovely definition. Just know what a radian is, and that's it. Okay. And this is how you find a radian. Okay. With that being said, we're going to find the length of an arc of a circle. So we are going to be given the arc length formula. For a circle of radius r, a central angle of theta radians subtends an arc whose length s is given by s equals r times theta. So one thing to notice here is that theta, if you don't know what I'm saying, you pronounce this as theta, which theta is a symbol that represents degrees or radians. Theta represents an angle in degrees or radians. But if you're ever going to find the arc length of a circle, theta must always, always, always be in radians. And yes, on the next page, we can convert from radians to degrees, and we can convert from degrees to radians. So if you're ever given the value of theta in degrees, when you're finding the arc length of a circle, you must always convert it to radians. So for this formula, theta must always be in radians. Okay. So example 1, find the length of the arc of a circle of radius 2 meters subtended by a central angle of 0.25 radian. Okay. So I guess before we dig into actual calculations, what we're looking at is basically just a circle. Here's our center, and we have the rays of the angle that intersect the circle, and we are given the radius r, and our goal is to find the length of this arc. So given the radius and given the angle theta in radians, we can go ahead and find the length of this arc, which is given by S. So that is just everything we are finding. We're just looking for S. So all we have to make sure is that theta is given in radians. And in this problem, theta is given in radians. So fair enough, we get S equals, and our radius is 2. So you'll have 2 meters times the value of theta. So it says a central angle of 0.25 radian. That is our theta. So you'll have 0.25. And then just 2 times 0.25, and we're going to get that the length of this arc on the circle is 0.5 meters. That's it. Nothing to it. Okay. And then number 2, same exact thing. Given theta is 1/4 radian, and given S is 6 centimeters, find R. So this time, they're giving us the arc length, they're giving us theta, and now we have to find the radius. So for these ones, S equals R theta. It wants us to solve for R, so I like to rearrange in terms of R. So to solve for R, all we have to do is divide by theta. So I'll say divide theta, and you'll get S over theta equals to R. So rearranging the formula is always important. It lets you know what variable you're solving for and how to isolate it. So all we have to do now is plug in the value of S and plug in the value of theta. So we'll get S, which is 6 centimeters, over theta, which is 1/4, equal to R. And now remember, if you're ever having a fraction in your denominator, you go ahead and multiply by the reciprocal, which means that when you multiply by the reciprocal, this becomes, let me get more room here. Let me see. There we go. Equals 6 centimeters times 4, because we multiply by the reciprocal of the denominator, which means our radius is 24 centimeters. All right. And that's it. That's finding arc length. Pretty straightforward formula. Just make sure theta is always in radians. If it is not, we must convert it to radians. And we will get into converting, I believe, on the next page. So degrees and radians have an important relationship. So we said earlier that 1 revolution was 360 degrees. Now that is in degrees. But what is 1 revolution in radians? And 1 revolution in radians is given by 2 pi radians. So a revolution in radians is 2 pi, a revolution in degrees is 360. So in order to convert from degrees to radians, we make a special ratio. First thing we do is we set 360 equal to 2 pi and divide by 2. This gives us that 180 degrees equals pi, which is all holding true because half a revolution in degrees is 180, which means half a revolution in radians must be pi. And then to make the ratio to convert from radians to degrees and degrees to radians, one thing you can do is divide by 180 degrees on both sides, and this gives us that 1 radian would equal pi over 180. Or if you divide it by pi, you would get that 1 degree is equal to 180 degrees over pi. All right, so those are the conversions, and they are right below for you. So in order to convert from degrees to radians, you would take whatever degree you're given, whatever degree you are given, and multiply it by pi over 180. And this would convert it to a radian. In order to convert from radians to degrees, you take whatever radian value you are given and multiply it by 180 over pi. And this will convert it from radians to degrees. Okay. So we will be using these unit conversions down below. And if you did not know, a radian is actually 57 point something degrees. So it's actually pretty cool. All right. What is it? It's 180 over pi, and 1 radian is approximately 57.295. So I'll put them all in there. 57.295 degrees. That just shows you how big a radian is to a degree, to 1 degree, right? If I did 1 degree, that would be 0.0017 radians. Crazy, right? So 1 radian is definitely a lot bigger than 1 degree. All right. All right, so now we convert from degrees to radians. So here I'm given 60 degrees. So all we have to do is take 60 and multiply it by pi over 180 and simplify. So you'll get 60 pi over 180, and we know 60 goes into 180 3 times, so we end up with pi over 3. So what we can say from this statement is that 60 degrees is the same as pi over 3 radians. And this is going to be helpful when we start building a unit circle. So you know how to switch back and forth between degrees and radians. And knowing how to switch between back and forth can actually make some problems a lot easier to deal with. All right, let's try it again. 150, multiply that by pi over 180, and you'll get 150 pi over 180, and you could take a 10 out, get you 15 over 18, or you could take what, a 30 out? I think if you took 30 out, you would get 5 pi over 6. Yes. Which again, we can say 150 degrees is the same as 5 pi over 6 radians. Okay, not bad. Negative 45 degrees, same thing. Multiply by pi over 180. Negative 45 pi over 180. And 45 over 180 gets us, let's see, it's 90, that's a quarter. So this ends up giving us negative pi over 4. And once again, make the comparison. Negative 45 degrees is the same as negative pi over 4 radians. Okay. So that's going from degrees to radians. Next, we go from radians to degrees. So we take pi over 6 and now multiply it by 180 over pi. Your pi's cancel, of course, right? Leaving you with 180 over 6, the degree symbol there. This is in degrees now. And 180 divided by 6 gives me 30 degrees. Which means pi over 6 radians is the same as 30 degrees. Okay. Keep going. 3 pi over 2 multiplied by 180 over pi. Your pi's will cancel, leaving me with, I can do, here I'll rewrite it without the pi's. I'll have 3 over 2 times 180 over 1. And we know that 2 goes into 180 90 times, and 3 times 90, we get 270 degrees. So make the connection. 3 pi over 2 radians is the same as 270 degrees. All right, last one. Negative 3 pi over 4 times 180 over pi. Pi's cancel, and then 4 goes into 180. What do we have? 45 times, so that's a 1. That's a 45. And 3 times 45 is negative 135 degrees. Make the connection. Negative 3 pi over 4 radians is the same as negative 135 degrees. Okay, and that's how you convert from degrees to radians, radians to degrees. Very helpful if you are given a radian value and you have no idea where it is on the unit circle. If you have no idea where a radian value is, convert it to degrees, and that should pinpoint it for you automatically. Okay. So the last one we found the length of the arc. Now for this one, we'll find the area of the actual sector. So what we're looking for in this one is, once again, given a circle, whose rays intersect the circle. Well, if we are given theta, and if we are given the radius, this means that given radius and given theta, we can actually find the area of this sector. That's what we're looking for. We're looking for the area. No longer the length of the arc. We want to know what is the area. If I took a slice of pizza, what is the area of that pizza? Nobody cares about the area of a pizza. Just eat it, right? Okay. So the theorem for the area of a sector, the area A of the sector of a circle of radius r formed by a central angle of theta, which has to be in radians. Make sure theta is in radians. If it's not in radians, you will get it wrong. Okay, and it's given by the formula A equals 1/2 r squared theta, where all we need to find the area is the value of the radius and the value of theta in radians. So for number 1, find the area of the sector of a circle of radius 2 feet formed by an angle of 30 degrees. All right, what is wrong with this problem? Well, I mean, nothing's wrong with it, but something needs to be done before we plug numbers in. They are giving us the angle in degrees. And remember, in order to use this formula, the angle must be in radians. So fair enough. All we have to do is convert degrees to radians, and we can continue with the problem. So we take 30 degrees and multiply it by pi over 180. You get 30 pi over 180, which will reduce to pi over 6 radians. Which means now we can plug into the formula because we have converted degrees into radians. So for A, you'll get 1/2 times, and the radius given here is 2 feet. So I'll put 2 feet squared and multiply it by my angle theta, which is pi over 6. We'll get 1/2 times 4 square feet times pi over 6, and then 1/2 of 4 is 2. So you have 2 square feet times pi over 6, which will give us 2 pi over 6, or pi over 3 square feet. And yes, if it did ask you to put it in decimal number, all you have to do is type in your calculator is pi divide 3, and we'll get 1.047 square feet. If it wants you to convert it to actual decimal number. Okay, once again, not bad. If you know the components, plug them in. But remember, theta has to be in radians. All right, 2. Given the radius is 6 meters and the area is 8 square meters, find theta. All right, this time we solve for theta. So remember the formula is A equals 1/2 r squared theta. We want to solve for theta, so let's rearrange the formula and get theta by itself. The first thing I'm gonna get rid of is this 1/2. In order to do that, I just multiply both sides by 2, which means I would get 2a equal to r squared theta. And then to solve for theta, I just divide off r squared. And we get 2a over r squared is equal to theta. So now you have an equation that helps you solve for theta by itself. So plug in the numbers that we need. We know the area, it's given. We know the radius, that's given. So this means that theta will be 2 times 8 square meters over 6 meters squared. We get 16 square meters over 36 square meters. Your meters cancel. And 16 over 36 reduces to what fraction? 4/9. So this means that theta is 4/9 radians. All right, awesome. And that's it. That is the formula to find the area of a sector. All right. And once again, if you wanted in decimal number, that would be what? 0.44 repeating radians. Okay. And now for some more formulas. Woo! All right, right. So many formulas. Chapter 7 is full of formulas. Trust me. Well, actually, chapter 8 has probably like 30 formulas. Good times, I know. Okay, so here we're going to cover linear speed and angular speed. So if you have something going around a circle at a constant speed, this is called linear speed and can be given by v equals s over t, where s is the distance traveled in time on the circle, and v is the linear speed. And, oh, t is time, yes. Then you have angular speed. So this object's going around the circle, but now we don't want to know the speed of the object going around the circle. We want to know what's the speed of the angle that's going with the actual object, right? So I guess diagrams are always good, right? So here's my circle, and then let's say my angle here and here, and let's say that this point keeps rotating around the circle. Well, we want to know what is the speed of that actual point, right? Or object. So that's what we're looking for. So let's just do this. And this is going to be, so you're given r, so it moves on the circle of radius r at a constant speed, and t is the time that it takes to go around the circle, and v is the actual speed. So s represents distance traveled. So you have r, s, and then t is the amount of time it took to go around the circle at that rate. So I'll just put t down here. Okay, so we're looking at how fast that object's moving. So for angular speed, there's my circle again. But this time, we're looking at how fast this angle is getting swept out as it moves along with the object. So how much of the angle is being swept out? So to know that, The angular speed, which is given by that fancy looking symbol that looks like a W, we call that omega. The angular speed omega of this object is the angle theta in radians, which is swept out over an amount of time. So here, theta is moving. And so this line represents theta being swept out over some certain amount of time, t. So we don't care about what distance the object is covered. We're cared about how fast is the angle moving as the object is going around the circle. Whew, okay. So those are those two formula. One gives you linear speed, one gives you angular speed, and now we have a third formula we can create that is an important distance between linear speed and angular speed. Okay, so look at this. So taking the linear speed formula, which we saw above, v equals s over t. Well, what we learned earlier is the arc length formula, which is represented by s. Arc length, which we learned, is given by the formula r times theta. Well, now we get r times theta over t. Well, if you rewrite this as r times theta over t, well, theta over t belongs to the angular speed formula. Theta over t can be represented by omega. So we get a new formula that is in terms of radius times omega. But we only use this formula if you read or see, well, seeing and reading, both the same thing, right? If you see these keywords, revolutions per unit of time. If you ever see those words, that is when you will use this formula. Revolutions per unit of time. All right, let me get rid of my playbook here. We scored a touchdown, now erase. So we get v equals r times omega. And we only use this formula, only use this formula if you see radians per unit time. So if the angular speed is given in terms of revolutions per time, be sure to convert it to radians per unit of time. And the problem will specifically say revolutions per unit of time, like you'll see it. So in order to convert it, you take whatever revolutions it gives you. In this example, we're given 900 revolutions per minute. To convert it to revolutions per radians, or actually radians per unit of time, we multiply it by 2 pi. Because we know that 2 pi radians is the same as 1 revolution, which means your units of revolutions will cancel, giving you 900 times 2 pi, which is 1800 pi, and the units that are left are radians per minute. So if you're ever given revolutions per time, you must convert and use this formula. If you do not see those words, revolution per time, then you use the two formulas above. Trust me, the problem will say. Just like this one. Finding linear speed. A child is spinning a rock at the end of a 2-foot rope. Y'all, let's talk about this child. Who's letting their child spin this rock on a 2-foot rope? I would be scared. All right, back to the math. All right, so the child is spinning a rock at the end of a 2-foot rope at the rate of 180 revolutions per minute. We have just seen it. We were given revolutions per time. Revolutions per time, which means we get to use that special formula of r times omega above. Okay, find the linear speed of the rock when it is released. Okay, so this means we get to use v equals r times omega. But before we actually plug into the formula, 180 revolutions per minute has to be converted to radians per minute. So let's start with that first. So I'll say convert. And we take our 180 revolutions per minute, and we multiply it by 2 pi radians. And like I said from the above, 2 pi radians is the same as 1 revolution, right? We learned that earlier. 1 revolution is 360 degrees or 2 pi radians. This is where that conversion comes from, right? And now revolutions cancel, and we are left with 180 times 2 pi, which is 360 pi radians per minute. 360 pi radians per minute. Now we have our omega. Which means come back to the formula. And V equals, we know the radius. If the child's spinning a rock at the end of a 2-foot rope, well, that radius must be 2 feet. So you'll get 2 feet times 360 pi radians per minute. Multiply those together, and you will get 720 pi. Since we know this is in radians already, we can drop the radians unit, and all we have to say is that this kid is spinning this rock at 720 pi feet per minute. But let's say we want to know what speed that is. Well, one, we're Americans. Do we know how fast feet per minute are? No. Right? Maybe we're all not Americans, but in America, we don't do anything by feet per minute. We go with that common rate of miles per hour. So let's go ahead and change 720 pi feet per minute into miles per hour, because that's what we do here, right? And I want to know how fast this kid's actually spinning this rock at. Okay, so we'll call this convert to miles per hour. So we have 720 pi feet per minute. Now this is for all you science heads, right? Well, in order to convert to miles per hour, first thing we need to know is how many feet are in a mile. And that should be 5,280 feet in 1 mile. Let me ask Siri. Hang on. Hey, Siri. Nope. How many feet are in a mile? Nope, she said nope. Okay. How many feet are in a mile? It's 5,280. Perfect. 5,280 feet. Now, we need to convert from minutes to hours. Well, we know that there are 60 minutes in 1 hour. We have our conversion table set up, and feet will cancel, minutes will cancel. All we have to do is multiply straight ahead. So what we have left is, and I'll show the multiplication, you'll have 720 pi times 60 all over 5280. And now this is in miles per hour. And I'm going to type it in my calculator just like I wrote it. And let's see how dangerous this kid actually is. Let's see, 720 pi times 60 over 5280. And this kid is spinning this rock at 25.7 miles per hour. Somebody grabbed this kid's parents. He's about to do some damage. And again, the reason to convert is because we don't do things in feet per minute. We have no idea how fast 720 pi feet per minute is. So why don't we just convert it to miles per hour? And now we're like, oh crap, this rock's gonna hit somebody at 26 miles per hour. Get out of the way. And that's it. Okay. Fun times, right? So once again, if you see those words, revolutions per minute, revolutions per unit time, you know that this means you get to use that special formula of R times omega. Okay. Last two questions. Applications. The arm and blade of a windshield wiper have a total length of 30 inches. If the blade is 24 inches long and the wiper sweeps at an angle of 125 degrees, how much area can the blade clean? I don't care, right? Okay, so I'll draw my diagram because diagrams are always important. So here's my windshield wiper. And the arm and blade of a windshield wiper have a total length of 30 inches. The blade is 24 inches long, which means the arm should be 6, right? So here is this is my wiper blade. So this is 24 inches, which means my arm is only 6 inches. And then it says the wiper sweeps out at an angle of 125 degrees. How much window area can the blade clean? Well, I guess the one thing it's forgetting here is also how much does the blade not clean, right? And this is going to fall under the area of a sector. This is going to use the area of a sector formula because we see we have sectors here. We have the area that the windshield cleans, and then you have the area that the blade cleans, and then you have the area that the arm cannot touch. So you have an uncleaned area. All right. Let's see. So let me erase that. Get rid of that. Get rid of that. Okay. So this means that we will have A equals 1/2 R squared theta. All right. Okay. So to see the total area that the blade can clean, you need to take the area that the blade touches and the area that the arm does not touch and subtract the two. That's it. Okay. But first, we see that we are given an angle in degrees. And if you're going to use the area of a sector, you must convert it to radians. All right, so fair enough. I'll say convert. And 125 degrees times pi over 180 gives me 25 over 36 pi, or 25 pi over 36. Okay, so let's find the area of the wiper blade, which means we'll call this area 1. And I'll have 1/2 times, and the, let's see, is it 30? Actually, yeah. To find the area that it cleans, you don't want the blade exactly. You want the area of the arm and the blade. So you're going to have 30 square inches times 25 pi over 36. And if I type this in, I get 30 squared times 25 pi over 36, and I get 981.75 square inches. And then area 2, I'd get the area that the blade cannot, that the arm cannot clean, which is the 6 inches. And once again, the reason we're doing this, why we chose 30 instead of 24, because if you chose 24, that'll give you the area, it'll just give you the area of the 24 inches, not the area that includes the whole windshield. So if you do the area of the 30 inches, you're covering the whole windshield. And if you subtract the area that we're not cleaning, then that zeroes in on the actual area that the 24-inch blade can clean. All right, if that makes sense. If not, we can touch it in class again. All right, so let me type this in. .5 times 6 squared, 25 pi over 36, and I get 39.27 square inches. Now, to find the area that the 24-inch blade cleans, all you have to do is subtract these two numbers. That's it. And I get 942.48 square inches. And this is the area that that 24-inch blade actually cleans. Let me just verify something. Oops. Nope, nope, nope. Yeah, if you type in 24 into this formula, it'll actually just give you 628 square inches, which is not true. So in order to zero in on what that blade actually cleans, you take the length of the whole arm and blade, which is 30 inches, you take the area of that and subtract it from the area of the 6-inch arm to get the actual area that that 24-inch blade can cover. Okay. Whew, that's fun. An object on a circle with a radius of 5 centimeters. An object is traveling on a circle with a radius of 5 centimeters. If in 20 seconds a central angle of 1/3 radians is swept out, what is the angular speed of the object and what is the linear speed? Okay. So those are going to use, a question like that is going to use the first two formulas. Linear speed, S over T, angular speed, theta over T. So first, let's go for linear speed. So for linear, it's V equals S over T. Okay. Well, we are given that the radius is 5 centimeters and an angle is, our angle is in 1/3 radians and time is 20 seconds. Okay, so remember that to find S is also that formula R times theta, because S is also known as arc length. So since you can convert it to R times theta, well, they're giving us the radius, which is 5 centimeters. They're giving us theta, which is 1/3 radians. And they're giving us time, which is 20 seconds. And all I'm going to do is type that into the calculator, just like I see it. And I get 1/12 centimeters per second. Okay. Angular, omega is theta over T. Well, fair enough. They give us theta. Theta is 1/3 radians. They give us time. 20 seconds. Do 1/3 divide 20, and you'll get 1/60th radians per second. And that's it. Those were probably the easiest formulas to use, right? You just have to know the pieces. And remember, linear could be a little tricky. If they don't give you S, remember that S is also the formula R times theta. And from there, they gave us radius, they give us an angle, and we're able to plug in those values. All right. That is it. There is one more page on here. It's about filling out the unit circle, but I can definitely cover that in class. We're going to want to use our own unit circle. We're going to want to fill out our own unit circle. We're going to want to know and love the unit circle, tattoo the unit circle on our face, forearm, hand, wherever you need it, right? But other than that, that was 7.1. That gets us introduced into some actual trigonometry. We learned about degrees and radians and how to draw angles today. All right. Till next time.